Hi. In this video, we will talk about another dimension reduction method, that is linear discriminant analysis. Let me just give you brief. We have used 5 features, right? That is CCV, that was concatenated with histogram, that was concatenated with moment features, that was concatenated with LBP features, and finally it was with HOG. So that was our concatenated feature vector. So in CCV we had a 27 color. So there were total 54 features, 27 coherence values and 27 incoherence. In histogram, we have a histogram of red, green and blue. Each histogram was of 256 bin. So total, when we concatenate all of them, that will become 256 plus 256 plus 256, that is 768. In moment features, we had total 4 different kinds of moment, that was mean, variance, skewness and kurtosis, and that we have computed for each channel. So there were total 12 moment, right? 4 kind of moment, and that is for each of the 3 channels. In LBP we have used 3 variant, and that was with radius 1 neighbor 8, radius 2 neighbor 16 and radius 3 neighbor 24. And for each of them we were generating the histogram of LBP features. So again the dimension of this would be same like 768. And in HOG we have converted our image into number of cells, the number of blocks. For each block we were having 9 different features and so on. Fine. So approximately we had I guess 11 by 15 number of blocks. No, 11 into 11 blocks, right? That was a square image, 10 by 10. So I guess we had 11 blocks in horizontal direction, 11 vertically, so 11 into 11. And in each of them, there were 9 different features. So that was something around the dimension of HOG. So if we find out the total, that was going to be something around 2920 approximately. It is a huge dimension. So we have applied PCA on that. And PCA is reducing it up to something around 2500, not exactly this, but it will be number around this. But still this 2500 is a big number to train the model or to compare it with 10,000 images. So what we are doing is, on this concatenated feature vector, we will apply LDA. Right? We will apply the LDA. Now LDA will give us the 99 features. LDA always returns C minus 1 number of features. That is, C is a number of classes. So right now we have 100 classes. So it will return only 99 feature for each image. Earlier it was 6000. PCA will reduce it to 2500 or something around, and LDA will fix it to 99. So both are dimension reduction technique. What is the difference? PCA is unsupervised technique. So PCA does not consider label information. It will just project the data in a way so that variance is maximized of projected data. Whereas LDA is a supervised technique. So it will also consider the class information, class label when we project the data. So this is more superior than PCA. Now let us see how it works, or what is the difference. Before that, we will understand something about the scatter of the data. Let us assume we have 3 different classes, M1, M2 and M3. And the small red points, green points and blue points are samples of that corresponding class. So these may be samples for maybe Mr. A. These all images are of Mr. B. These are the all images of Mr. C. Then these bigger circles are the average or the mean of that class. So M1, this point is mean of all the faces which are in red. These are the green is the mean of all the green samples, and blue is the mean of all the blue samples. So M1, M2, M3 are the class mean. Whereas this black circle is a global mean. So M is a mean of all the points, or you can say M1 plus M2 plus M3 divided by 3. Or you can add all the pixels of red plus green plus blue and divide it by total number of pixels. That will also give you the same one. Omega 1 represents class 1, omega 2 is a class 2, omega 3 is a class 3. So let us consider he is a Mr. A, he is Mr. B, he is Mr. C. And we have different images of that particular person. You know well how to compute mean, right? If there are n samples in any data set vector, then we will sum up all the xi's into that vector and we will divide it by total number of sample, that is n. So first you sum up all of them and divide it by n, that is the mean. Based on this, now we will construct or understand the notion of scatter. So there are three types of scatter. Within class scatter, that means how data within individual class are far from the mean, how far they are. So if scatter is less, that means points are very close to mean. If scatter is big, that means points are very far from the mean. So we will have a three scatter for class 1, class 2 and class 3. And when we add all of them, we will get the total within class scatter of the data set. Right? So what we are doing is, we are just doing this I minus 1 to c. C is number of classes. So right now we have 3 classes. So this will iterate 3 times. Right? C is equal to 3. Within that, what we are doing is x belongs to omega I. So I varies from 1 to 3. So initially it will fetch all the samples from omega 1. For all the samples, we are doing x minus m1 into x minus m1 transpose. So this is nothing but it's a square. So we are basically computing the variance. Right? X minus mi whole square. If it is in matrix format, then it would be transpose. If it is just a number, then it is same. You can simply square this term. So we are picking this x and we are subtracting mean from that, taking the square of that. Then we are picking second x from same class, we are subtracting mean of same class, and then we are taking the square of that. So for all red points, we are repeating this process and we are keep summing that difference, square difference. Then I will be 2. So now this will become omega 2. Right? So now it will pick up all the samples from green class, and this also will become now m2. So from each sample from green class, we have to subtract mean 2. Right? So this minus this whole square plus this minus this whole square plus this minus this square. So this we are repeating for all the points in green class. Then I would be 3. So here the class would be now omega 3, and here that would be m3, m3. So from all the samples of class 3, we are subtracting m3. So this will be subtracted. So what we are doing is ultimately we are computing the scatter of class 1. We are adding it to scatter of class 2. We are adding it to scatter of class 3. So we will get total within class scatter. Now see, if within class scatter is small, then that is good. Fine, because if this is the mean and if scatter is small, then all data points will be very tightly placed near the mean. Okay, something like this. So class separation would become easier for us because all points are very close to each other. So they exhibit almost similar kind of properties. So we won't have much difficulty in discrimination, right? But if class scatter is more, then what happens? We have one mean here and its data might be scattered like this, far away from mean. We have another mean here and its data might be scattered something like this. We might have the third class mean here and its data might be roaming around like this. So some of the portion would be mixing up for all 3 classes. So if any point is coming here, then it would be difficult to judge whether it is in class 1, class 2 or class 3. But here it is very straightforward. Even if some point is coming here, it is very close to mean 1. So we can easily say that, okay, this point is definitely from class 1. If something is here, it is class 2. Something is here, class 3. Right? So it is expected that within class scatter should be as minimum as possible for the better classification. The next term is a between class scatter. That means how far individual class means are from each other. That scatter we are computing. So this is our mean of all the means. So how far this means from global mean. That is what the within class scatter. That will tell you how far individual classes are from each other. That should be maximum. If suppose this is my class mean, okay, this is mean 1, this is mean 2, this is mean 3. So they are very close to the global mean. So when we consider about the points around this, they might overlap with each other. But if this is my global mean, if class mean 1 is here, class 2 mean is here and class 3 mean is here, they are well separated, then we don't have to worry. Even this within class scatter is more, then also it is fine. Fine, because we know that this sample is gonna be very far from samples in this class. So basic target is what? To maximize the between class scatter and to minimize the within class scatter. If we can do that, we will have the best projection of the data. they are well separated and we can easily classify. There will be less chances of misclassification. So how we compute it? I is equal to 1 to C. C is the number of classes. So this loop will iterate 3 times. Ni, initially this will be N1. N1 indicates number of samples in class 1. Mi minus m, so that will become m1 minus m into m1 minus m. So this is a square. Plus I will be 2. So this term will become N2. N2 indicates number of sample in class 2. So in that case, we are considering the mean. Mi will become m2 now. M2 minus global mean plus number of samples in third class, mean of that class minus global mean. When we do this, we will get the between class scatter. So ultimate goal of LDA is to project data in such a way so that this scatter, within class scatter will be reduced and between class scatter would be maximized. Got it? So that is the optimal condition. PCA was not looking anything. It was just trying to increase the variance. Now increasing variance is not always the solution. Right? When you project the data, PCA was simply looking to increase the or maximize the variance of projected data. But sometimes that is not sufficient for the classification, or sometimes it might lead to some poor result even. And total scatter is given by addition of these two, or you can rewrite the formula in this way. I is equal to 1 to capital M xi minus m into xi minus m transpose. So now we are computing scatter of each point with respect to global mean. This minus this square plus this minus this square plus this minus this square. We'll do it for all red, we'll do it for all green, we'll do it for all blue. So when we do it for entire class, we will get the total scatter, or you can add SW plus SB and you will have a total scatter. Fine. So let us first understand why we need a PCA, or why we need LDA, or what are the limitations of PCA. So PCA is unsupervised algorithm since it ignores the class label. That was the first thing I discussed. Goal of PCA is to maximize the total variance of projected data. Right? That's the goal of PCA. But it is not always desirable that you do that. Right? In contrast, PCA, LDA is supervised approach. Now see, if we consider the second point, that PCA always try to maximize the variance. If I project this data on this axis, similarly, when I project this data on axis, so my total scatter is like this. Okay, this much is the scatter. If I project it on this axis, or if I project it on this axis, then my total scatter might be less, because this will be the scatter in this class, this will be the scatter in this class, my total scatter might be less. But what is the problem? When you try to project in a way so that variance is maximized, here you are getting lots of mixing of the data. Right? Both the classes are being projected on a same axis. And so there will be very difficult when a new point is coming, you want to classify, you will project it here, but it is already an overlapping region. But here it is advisable. See, here both the projections are separate. So if some point is coming here and when you project it, it is being projected into the region of class 2. If something is here is coming, it is being projected in region of class 1. But here the variance of the projected data is less. Here variance of projected data is more. So PCA will project on this axis, not this. Clear? So PCA is actually misleading. It will increase the misclassification. But what LDA does? LDA will try to maximize the within class scatter, between class scatter, and it will try to minimize the within class scatter. So if it knows that if I project it here, then all class samples will be very closely placed to each other compared to this. Right? So here I can decrease the between class scatter. Between class scatter will be very small. That's what it is expected. Fine. So according to that, it will choose the directions. So this could be our LDA 1, LDA 2. So these are the vectors, LDA vector 1, LDA vector 2, etc. LDA finds the direction which maximizes the separation between multiple classes. Right? So here now, instead of variance, it will look for the class mean. That class mean should be as far as possible from each other. So here the projected class mean is somewhere here, it is here. But if we project it on this axis, then class mean of this would be somewhere here. Class mean of this would be somewhere here, very close to each other. Right? So we are not able to separate them properly. But if we project it here, then we are getting the maximum distance. So this axis will be the first choice for LDA. So class information it is considering. LDA achieves the optimal projection direction by maximizing the ratio of difference between projected class mean to within scatter class. So what it tries to do? It tries to maximize the ratio of what? Between class scatter. Between class scatter should be more, and within class, sorry, between class scatter should be more, and within class scatter should be minimum. So ultimately we are trying to do this SB upon SW. This we want to maximize, because this we are trying to minimize, this we are trying to maximize. So if this term goes in denominator, then that will be inverse. Right? See what our goal is, SB and SW. Within class scatter we want to minimize. That should be minimum. So all the projected data will be very close to each other. And between class scatter we want to maximize. So if you want to, either we have to convert both of them into minimization problem or maximization problem. So if I put this S, so SW I'm minimizing, that means 1 by SW I should maximize. Right? If you are reducing X, that means 1 by X you are increasing in direct way. So SB upon SW, this ratio we will try to maximize. That is what the ultimate goal of LDA. So what are the steps for that? Now it is pretty simple for you to understand. We have samples like this: x11, x12, x13, x14 up to x1n1. This is x21, x22, x23, x24 up to x2n. Fine, and xc1, xc2, xc3, xc4 up to xcnc. So we have c number of classes, and in each class we have some n1, n2 up to nc number of samples. So this could be variable. In first class you can have a 10 image, in second you can have a 7, in nth you can have a 100 image. That is possible, and that is why we have here n1, n2 up to nc. So that indicates number of samples in that class, and this xc term here, xc term indicates which class you are referring. nc indicates how many images in that class, and xc indicates how many which class we are referring. So this is class omega 1, class omega 2 up to class omega c. That many classes we have, and each image is of dimension n by n as we assumed in PCA. Next step, we have to find out the class mean. So we will add up all the images of class 1 and we'll divide it by 1 by n1. n1 indicates number of images in class 1. So we will get m1, mean of class 1, that is again a size of n by n. For computing the mean of class 2, we will add up all the images of class 2 and we'll divide it by total number of images into that class, that is 1 by n2, and we will get the average face for that particular class only. So ultimately what we did, we have added all the red points divided by number of red points, so that will get the mean of red class. Then we added up all the green points, and we have to taken the average of that. Similarly, we will repeat for all the classes. So in cth class we have a 1 nc sample, so we will divide it by 1 by nc, and we will add up xc1, xc2, xc3 up to xcnc. So that will give us this face. Right? So what is the first step? We have to compute the mean of every class. It is not applicable to image only, it can be numeric data also, but visually it is more appealing, we can easily understand. That's why I have taken the example of images. Next, now we have to compute the within class scatter. So you know that how to compute within class scatter, right? Within class scatter is given by x minus mi into x minus mi's transpose. Okay? So we will subtract the mean of each class from the sample of that class. So we will do x11 minus m1 whole square plus x12 minus m1 whole square plus x1 minus m1 whole square. So that will give us the S1, scatter of first class. Then I will take I is equal to 2, so I will get S2. So S2 will be x21 minus m2 whole square plus x22 minus m2 whole square plus x2n2 minus m2 whole square. So I will keep varying this I c times because I have c classes. So finally I have a SC. So SC would be xc1 minus mc whole square and so on. So I have S1, S2, S3 up to SC. I have C classes, so I will get C within class scatter for each class. Then I will simply sum up all the SIs. I is equal to 1 to C. If I have a 10 class, then I is equal to 1 to 10. And whatever SI I have computed here, that I am simply adding S1 plus S2 plus S3 up to Sn. Right? So here I have unfolded the equation. In earlier, when we saw the equation, it was like that SW is equal to summation over I is equal to 1 to capital C. Fine, it was together. Now I have just bifurcated that. First I'm just computing the inner term I times, and then I will simply sum it. So both are same, don't get confused. And yeah, let me just erase this. This dimension of Si would be n square by n square, because this is n by n, right? So it will be converted into vector, and then it will be multiplied. So that way vector will be n square by 1, that is this, into again the another transpose of that vector. So that transpose will be 1 by n square. So ultimately that is Si is going to be of dimension n square by n square. So within class scatter would be of dimension n square by n square, remember that. Next is we have to compute the global mean. So how we compute global mean? 1 by capital M. M is a total number of training image, and we have to sum up all the images of all the classes. So x11 plus x12 up to x1n1 plus x21 plus x22 up to x2n2 plus xe1 plus xe2 up to xenc. We will add up all the faces in database, and that will give us the global mean. Okay, so here it is shown formula for the global mean. Next we have to compute the between class scatter. And how we computed between class scatter? Class mean minus the global mean. We'll take the square and we will add up it for all the classes, and we will weight it by the number of images into that classes. So n1 into m1 minus m whole square plus n2 into m2 minus m whole square plus nc into mc minus m whole square. So that is the formula, and that will straight away give us the SB. So here also it is same. M1 is a n by n, but when we convert it into vector, that will become n square by 1, right? So this vector is of dimension n square by 1, minus we are doing the same n square minus 1, so that will remain same n square by 1 only, and that we are multiplying with the transpose of that, so that will become 1 by n square. And when you multiply these two terms, this one will be cancelled out. Dimension of final vector or matrix would be n square by n square. So SW is also of that same size, and SB is also of the same size, n square by n square. And what we are doing is we are seeking the matrix W which maximize the J of W, that is our cost function. That would be, or the projection axis, that would be W transpose SB upon W, W transpose SB W. So columns of W are eigenvectors. So what we are doing is basically we are projecting SB and SW onto the eigenvectors. Fine. Columns of W are eigenvectors of SW inverse and SB. So if we take this SW in numerator, then obviously we have to take inverse of that. So SW inverse SB. We have to find out eigenvector and eigenvalues for this. Fine. Like earlier, we did it for a covariance matrix C in case of PCA, if you remember. Right? It was returning me eigenvectors and eigenvalues. So here also it is going to be same, n square by n square. Training feature vector. How we will compute the training feature? That is xt. X is what? Our training matrix, which was of dimension n square by m. If you remember, there are m images, and each image is converted into vector, and the size of one image was n by n, so it will be vector of n square by 1, and we have such m images side by side, so the dimension of x would be n square by m. We are taking the transpose of that, so that will become m by n square, and whatever we are getting eigenvector, it will have a n square by n square a dimension. Fine, that is too big. But in LDA we have to choose only C minus 1 projection axis. Remember that. It is always fixed in LDA. You don't have any other choice. You have to always choose the number of eigenvector is equivalent to number of classes minus 1. So now out of n square we are selecting first C minus 1 eigenvectors which are having the highest eigenvalues, obviously. So when we compute this n square will be cancelled out. Dimension of final feature vector would be m by C minus 1. So m is the number of training image. Suppose we have a 10,000 image, then that would be 10,000 into C minus 1, that is number of dimension. Fine, C is the number of classes, that is 100. 100 minus 1 is 99. So you see that for each of the 10,000 image, we got 99 features only. Same we have to repeat for the test image. So for test image, we will get the dimension 1 by 99. Now this 99 dimensional feature vector, we have to compare the 99 dimensional 10,000 images. Whichever is the closest one, that will be given as an output. So this was all about theory part of LDA. I hope it is clear, right? No need to go into the tough mathematics. It's a simple explanation that you will ever find in any literature. So if you understood PCA properly, it is not difficult to understand LDA. But why LDA is effective? Because it utilizes the class information as well, and it will try to project the class mean in such a that they are as far as possible, and that's why there is a less chance of misclassification, whereas PCA was blindly looking for maximizing the variance. That's it. And that is why there were chances that in some cases in grid of maximizing the variance, classes were projected together on particular eigenvector. So that was not helping in proper classification. So that was all about theory part. In next video, we will talk about the code of PCA, LDA, and our final feature vector. Thank you.